as a testament to my own cheapness, I just put some paper over the old problem for the aqueous dissociations, and I'm going to start with phosphoric acid this time. Phosphoric acid is triprotic, and it's going to be a 3-step dissociation. What you find out is that like nothing happens down here essentially, and very little even happens here. We have a H3PO4 turning into H2PO4 minus, barely. We have H2PO4 minus turning into HPO42 minus, unfathomably, barely. And then HPO42 minus turning to PO43 minus, for all practical purposes, not at all. And what I want to do is I want to solve it in general to save some button mashing, and then we'll go back and plug the numbers in. And the reason I want to solve it in general is because these are the same every single time, okay? So we're going to do what we've always done. 0.500 molar is our starting amount. Not worried about it. 10 to the minus 7th molar from the autoionization of water, and 0 because we haven't made any yet, all right? 0.500 molar of that. Now, since that is weak, we know because of the K value, we're going to lose some unknown amount. Correspondingly, we're going to gain some unknown amount in each of those places, and we're going to have 0.500 minus x, x, and x. And the question always comes up like, well, when does the 10 to the minus 7th matter? Well, if you solve for x and you find out it's close to 10 to the minus 7th, go back and call this 10 to the minus 7th plus x and recalculate over here with your calculator. So I'm going to make a note here. This is going to end up x squared over 0.500 minus x equals 7.5 times 10 to the minus 3, and x equals some number. I don't care what it is right now. We'll need it later. But the key is, when I carry on to the next step, when I'm doing ice here, I have an amount of H3O plus when this starts to dissociate, and that amount is x. I have an amount of H2PO4 minus when this starts to dissociate. That's in fact where it came from. We have x of it. So in this next dissociation step, we'll set up our ice once again. Initial change equilibrium. We are going to have none of this starting out. I do have some of this and this from our previous dissociation. It is weak, so I'm going to lose some unknown amount. I already used x, so let's call it y. This will have to go up by y, and this will have to go up by y. And so we get x minus y and x plus y and y for our amounts at that point in time. So theoretically, our Ka2 is going to be x plus y times y over x minus y. And that should be equal to 6.2 times 10 to the minus 8th. But I'm not going to write it right there because there's something we saw in the previous video that I want to look at right here as well. But again, I'm not going to solve for whatever y is. That's a concern for later in the video. I'm going to solve it in general first. And as I said, that's because every single one of these is the same, and there's some trends we can save ourselves for later. All right. We are carrying down these amounts right here. So our H3O plus is getting carried down as x plus y. Our HPO42 minus is getting carried down as y. This is a stepwise dissociation, right? And if you're looking at all these little typos here, it's been a rough day. Anyway, in this particular case, since it is weak, we're going to lose some unknown amount, and we'll call that unknown amount z, since we already used x and y. We'll gain z, and we'll gain z. And so down here we have y minus z, we have x plus y plus z, and we have z. So now we've got all our amounts at equilibrium, and z is going to be some number here. This is supposed to be x plus y plus z times z over y minus z. And that's supposed to be equal to our 3.2 times 10 to the minus 13th. So at some point in time, we'll have a number z equals, right? And it would be nice if we could cut some corners and save some button mashing. But for right now, we're going to look here. And we use some program like Solver in the calculator to plug this quadratic in. And we find out that x is 0.058. And I'll write that as, in fact, I don't really know if I want to do that in a different color. 5.8 times 10 to the minus 2. So that's what x is. Now, x plus y times y over x minus y equals this is what's going to get us our y value. And if you remember from the previous video, there's a very important relationship we need to make. And that relationship is we started with 0.5 of this, and now we have 0.058 of this. This is even worse at dissociating, so we're going to get some exponentially smaller number for y. So we're going to utilize that technology. In fact, I'm going to put it right here. The x value is going to be much greater than the y value is going to be much greater than the z value. And that's going to save us some work here. So this is essentially going to be x over x times y. X plus y, we'll say x plus y is going to be x, and x minus y is going to be x. So when we set that up, we end up with x times y over x, which is y, which is 6.2 times 10 to the minus 8th, this kW value. All right, so y is 6.2 times 10 to the minus 8th. And if you doubted me before, you can look and say 0.058 plus 0.000000062 is 0.058, so x is perfectly reasonable to ignore that y. Then down in this step, we'll see if we can make some similar type of shortcut, and we'll do that by saying that x right here plus y plus z is for all practical purposes x, okay? And y minus z, since y is much greater than z, is for all practical purposes y. So in this particular case, we end up with this turning into x, this turning into y, and then we have z. So it becomes xz over y. And we can do some rearranging here since we know this equals 3.2 times 10 to the minus 13th. And then z equals the kW3, or sorry, Ka3 times y divided by x. And that actual value is 3.4 times 10 to the minus 19th, which is a pretty small number. So as you note, not a very big number. Wow, that's small. Oh my gosh, that's really, really small. So this one doesn't really come into play in that x plus y and that y minus z and everything else. So I'm going to write that stuff over here, what is in our final solution. And the strategy I suggested before, so spoiler alert, we're going to end up going down and across to get our equilibrium amounts. It's going to be this, and this, and this, and this, and this. In fact, circling those wasn't super helpful. So we'll say this, 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 because we're just going down and across. It's the last time we see those things. H3PO4 I never see again, so that's the number I'm going to have to use. H3O plus I see again later. In fact, I see it again later, so the last time is the time I'm going to have to worry about it because it changes in between. H2PO4 minus I see again here, so this number isn't going to be the final number. I need that one, right? HPO4 2 minus I see again here, so that's the final number, and then we end up with just that. So we've got 1, 2, 3, 4, 5, and hydroxide gives us 6 things in the final solution. And I don't know how motivated I am about color coding these, not very. So at equilibrium, we're going to have what we said there, which is the H3PO4, and I'm just going to keep chopping off H's. H2PO4 minus, HPO4 2 minus, PO4 3 minus, H3O plus, and whenever you have H3O plus, you also have to have OH minus. You can't have one without the other. That is what our KW expression says. And we'll get that as KW over the concentration of H3O plus. All right? I did brackets since we're looking for concentrations. And we'll see if I can line things up a little better here. I'm going to skip these over and we'll leave some room right here so that our actual concentrations we can put over here. H3PO4, and luckily, I mean, I labeled things pretty cleanly. It's supposed to be 0.500 minus X, right? And that's 0.500 minus 0.058, which should get us 0.44 approximately. 0.44 molar H3PO4. All right, H2PO4 minus is supposed to be X minus Y, right? But Y is really small compared to X, so that should just be X, which is 5.8 times 10 to the minus 2 molar H2PO4 minus. Our HPO4 minus was supposed to be Y minus Z, which we said since Y is so much bigger than Z, it's just going to be Y. And Y was 6.2 times 10 to the minus 8th molar. In this case, HPO4 2 minus. Our PO4 3 minus is supposed to be Z, and Z is 3.4 times 10 to the minus 19th, which for all practical purposes is none. And then H3O plus was supposed to be X plus Y plus Z, which we established would just be X because X is so much bigger than Y and Z. And X was 5.8, 10 to the minus 2 molar. Calculating our KW over H3O plus, that was 10 to the minus 14th over 5.8 times 10 to the minus 2. We end up with a hydroxide ion concentration of 1.7 times 10 to the minus 13th. And that is our answer to part A. For part B, from before I just asked for a pH, and we can calculate that pretty quickly. pH is supposed to be the negative log of our concentration H3O plus, and in this case that's the negative log of 0.058 approximately. And that pH is 1.24. And that is our answer to part B right there. And I'm flipping back here to see if we can see it, but H3PO4 had a K value of 7.5 times 10 to the minus 3. It's a weaker acid. In fact, maybe I can just write this down. H2SO4 is what we started with, then we did H2SO3, and then we did H3PO4. When we set these up, we had 0.500 molar of each, and we ended up with a pH value for each of these. The pH for our sulfuric acid was 0.24. The pH for our sulfurous acid was 1.11. And the pH for H3PO4 was 1.24. And that's no surprise since you started with the same concentration. Since the strength of these acids is going down, the pH is going up, right? So our strength went down, which gives us a pH that is going up. So this becomes less acidic as you go down. All right, that's what you'd expect. 0.5 for a weaker acid, and we can tell based on those K values, Ka for H2SO4 was large. Ka for H2SO3 was 1.4 times 10 to the minus 2. And Ka for H3PO4 was 7.5, 10 to the minus 3. So the pHs are going up as the K values go down because those things become less acidic regardless of their polyprotic or not. The end.